Hi, welcome to Chapter 7, Periodic Properties of the Elements. Overview Part 1, where we're going to go over the development of the periodic table and how to calculate effective nuclear charge. The periodic table was developed by Mendeleev and another man, Meyer. They both kind of came up with the same idea at the same time and published their results. As it turns out, Mendeleev is kind of credited with the development of the periodic table because he kind of pushed for it a little bit more than Meyer did. But basically, they used the principle that elements in the same group, a group is a column, have similar properties. The properties are not identical, but they are similar. So one of the other things that Mendeleev was able to do was he left blank spots in the periodic table and predicted where elements should be that haven't been discovered yet. And he was able to predict the properties that they should have. And then once they were discovered, it was found that they kind of closely tied into what he predicted, if you look at this table here. So that gave the periodic table a little bit more credit. When Mendeleev was developing the periodic table, he had to use atomic masses because atomic number wasn't really discovered yet. It wasn't until about 35 years later when the nuclear atom was discovered by Ernest Rutherford. And then Moseley developed the concept of atomic number and kind of adjusted the periodic table slightly and based it on atomic number. So our current periodic table, if you look at it, it is ordered in increasing atomic number. And when you look at that, there are certain patterns that develop within the periodic table. And that's called periodicity, a repetitive pattern of a property for elements based on their atomic number. And some of these patterns that we're going to be studying is the size of the atom and ions, ionization energy, which you might remember is the energy to remove an electron, electron affinity, and then some trends that happen within groups in the periodic table. Okay, but in order to discover, to understand why these certain patterns arrive, we kind of have to understand what's going on within the atom in our elements. So there's something called an effective nuclear charge. Your regular nuclear charge would just be your number of protons. That would be your nuclear charge. But what happens is you have an inner core of electrons that actually are repelling your outer electron here. So because there's these repulsion forces between here, they kind of shield this outer electron from feeling the pull of the nucleus. So when you're calculating your effective nuclear charge, you have to take into consideration your inner core electrons. Because you can kind of see here, there's a lot of electrons in this area, and they're kind of shielding the electron that would end up here from feeling the positive pull of the nucleus, right? Because there's a couple forces going on within your atom. There's the attraction between your valence electrons and the nucleus. So that's one force. And the second one is electrons repelling each other. And these two forces kind of contradict each other or work against each other. So the force that your valence electron feels depends on both the repulsions and the attractions that are going on in the atom. So how do we kind of estimate an effective nuclear charge? And the variable that is used for effective nuclear charge is Z effective. So a rough estimate with a lot of assumptions that kind of gives you an idea of the effective nuclear charge, but is not really wholly correct, is to take the Z, your number of protons, minus your inner core electrons, the number of inner core electrons. And that will give you your effective nuclear charge. And if you do this, as you go, if you look at this graph here, as you go across a period, it's going to increase. Z effective increases as you move across a period. As you go down a group, it also increases, but just very little. And what you need to realize is if Z effective increases significantly, then your valence electrons are more attracted to the nucleus. So your force of attraction increases if Z effective increases. So let's practice calculating some Z effectives. So here we have magnesium and phosphorus. Okay, and it says write the electron configuration. So magnesium has 12 electrons. So it's 1s2, 2s2, 2p6, 3s2. And we want to calculate Z effective. So if it has 12 electrons, it also has 12 protons. Minus my inner core. Here's my inner core electrons, which is 10. And that gives me a positive 2 effective charge. For phosphorus, okay, it has 15 protons minus my inner core. So anything that's on the same energy level is not considered your inner core. And this gives you plus 5. Now, if you look at the periodic table, phosphorus is, so here you have magnesium, and then you move across and you get to phosphorus. So as you're going across, your Z effective is increasing. And in your Chem 1 days, we talked something about your nuclear charge. Because as you go across the periodic table, there are certain trends that occur. And it's related to what we used to say was your nuclear charge. But really, even it's related to your Z effective. So because the Z effective increases as you go across, there is a greater force of attraction between your valence electrons and the nucleus. Because what's in the nucleus? The protons. Now, what assumption is made about the core electrons when we solve for Z effective this way? We are assuming all core electrons repel the same amount. And this is an easy way to estimate it. But it is not 100% correct. So another approach, this man named Slater came along and he tried to improve it. And he said if you have elements that do not have D and F orbitals, you could kind of use this approach. Where if you have an electron that is higher than the electron that you are trying to calculate Z effective for, it has an S of 0. If you are in the same energy level, its S is 0.35. And if you are one level even lower than that, it's 0.85. And then one level lower than that, it's 1. So what do these numbers mean here? So why don't we do an example? So again, we have our magnesium. And remember, the original way we calculated it was we did 12 minus 10, and we got plus 2. This was the original. So now let's try it in this Slater the Slater method. So we still have 12 protons, and we're going to subtract now. Here is the 3s, and we are interested in one of the electrons on the 3s. So there is still one electron there. So 1 on the same energy level times 0.35. Plus, on the second energy level, we have 6 plus 2, we have 8. So that would be 8 times 0.85. And then on the first energy level, even further away, we have 2 electrons, and that would be 2 times 1. So when we add all that up, we end up with a plus 2.85. So it is close, but there is some adjustment here. What Slater considered is that not all electrons are repelling the same way. And it depends on how close your electrons are to the electron that you are interested in. Notice. And then it depends on how close they are to the nucleus. So let's do the same thing for phosphorus. So remember, phosphorus was 15 electrons. Okay, and the original way that we did Z effective was we took 15 minus 10, and we got plus 5. So let's do the Slater method. We still have 15 protons minus. So here we now have, there's 5 electrons on the third energy level, but one of them is the one we're interested in. So that means there are 4 on the third energy level that get multiplied by 0.35. Plus 8 on the second energy level. Plus 2 on the first. So then when you do all that math, you get plus 4/8. So in this case, the Z effective is a little bit lower than what we estimated here. Either of these techniques still give you the general trend that as you move across a period, Z effective increases significantly. And that is the end of part 1.